Okay, so now we're going to be discussing hash tables. Essentially, what hash tables is that we're going to access or store the records in an array and have direct access to those records when we need them. And basically, it involves the use of a hashing function. This hashing function will take input of a key field that we have chosen. And obviously, for each record or each data item that we're entering into our table, for our array, it is important that that key field remains unique. So that unique key field will allow us for data, for the collision of data to be reduced. Now, what is collision? We'll be looking into that in a bit. First of all, if you want to store records in an array and have direct access to the records, we can use the concept of a hash table. The idea behind a hash table is that we can calculate an address that is the index, array index. So basically, when we're talking about the addresses, we're talking about an array index. So when we're talking about the index positions, our addresses, we mean the index positions. From the key, we value the record and store the record at this address. So whenever we search a record, we calculate the address on the key and go to the calculated address and find the record. Calculating an address is called hashing. So we have studied hashing in paper 3 in a bit. So basically now we're going to be elaborating this concept of hashing using what is known as a hash function and so on and so forth. Finding a hash function that will give a unique address from a unique key is very difficult. If two different key values hash to the same address, it is called the collision. So this is what we're talking about. If, say, for example, I'm entering two key fields and they end up having the same index position to be stored, this problem is known as collision. Now, dealing with collisions allows us, we could do it three different ways. One of them is known as chaining. In chaining, essentially what we do is that we create a sort of linked list type structure, and this linked list is sort of like how we've seen linked list before. Sorry. Like this is our array of your nodes. Now these are the start pointers. So let's just say, for example, this is one node right here, and this is another node right here. And these nodes are all having the same index position. So this is a node, and essentially these nodes are linked together, starting from index position, this one right here. So it's connected this way. So if it's, for example, zero index, all of the nodes that lead to zero index will be connected as a chain here. And all the other nodes that are also connected with the one index will have another chain over here. And all nodes will have an index position 2 will be connected in another chain, so on and so forth. So this process is known as chaining. So essentially what you're doing is that you're creating a linked list of all the nodes which are supposed to have the same index position. And basically you're dealing with indexing in this way. Now, this is not actually, relatively, easy to concept, because of course, for this to be implemented, you need to understand what linked lists are. So if you are familiar with linked lists, then you can do this very easily. But however, if you're not used to linked lists, then there has another method, which is known as open hashing. We'll be looking at open hashing algorithm in just a bit. But before that, what we can do is we can use another technique, which is known as closed hashing. Using overflow areas, all collisions are stored in a separate overflow area known as closed. So basically, we have a logically separated area in your in your array that is meant to store a duplicate in the or colliding positions. So if, for example, you're trying to find a value that is supposed to be stored in a particular place, if it's not there, then most probably, if it does exist in the array, it's going to be stored in the closed or the overflow area. Okay, so most commonly used technique in your course as well is known as open hashing. Now, this is actually a pretty simple concept, and it doesn't require the knowledge of linked list, and you don't have to create a separate overflow area. But what you have to do is basically allow for some sort of linear search. Linear search is happening in this concept as well, but linear search for only small amount of time, you have some linear search to take place with respect to hashing. Now, to understand open hashing, let's consider this example over here. Assume that we want to store customer records in a one-dimensional array by the name of by the name of hash table. Now there will be 0 to n elements, so we're using index position 0. Okay, the key field that we're going to be using in this example is the customer ID, and the customer ID ranges from this value to this value. So basically, we can have these 5 digits customer value IDs, and a lot of values are allowed here. So any customer which is part of the system can have one of these values. Okay. Now, basically, for hashing to work, we have to have a hash function. So as you can see here, this is my hash function. What the hash function does is that it takes as a parameter the key field, which in fact is my customer ID. That customer ID is operated in this way. So basically, this is my hash function. So we take the key field that's entered, which is, by the way, this number right here, at any one of these numbers over here. We take the mod of that value, and the mod what? 10. So for example, if we have 9 elements, if our array is 9, so we will take the mod 10. If we have 11 elements, we will take the mod 12, so on and so forth. So if, for example, we're choosing an array size of 9, so in that case, we will take a mod 10. So our hash function states that mod n plus 1, whatever the value, the size of the array is, we'll be using that value plus 1 as the mod value. So for example, if we're using an array of size 9, as you can see here, start from 0 all the way to 9. So 0 to 9. If we're using an array of size 9, our function will become 9 plus 1 mod 10. So in that case, our hash function will become the customer ID mod 10 will return an index position value of where that array is supposed to be stored. Now, based on the first index ID position that ID value that I have, the key field I have, this is 45876. So if I enter 45876 into this function over here, and by the way, these are only 0 to 9 values, so that means I'll be using a mod 10. So in that case, 45876 mod 10 will result in index position 6. So basically the answer for this function is 6. So index will have 6 in it. So technically, based on my hash function, the value of my value for my the index value for my ID will be index position 6. And I have stored this 45876 in index position 6 over here. Similarly, if we use 32390 and take the mod 10 of this, mod 10 of 32390 will result in 0. So that's why we have 32390 address stored here. Similarly, 95312 will result in index position 2 based on this function over here. And that's why 95312 is stored at index position 2. Finally, this is where the problem starts. Now, as you can see here for the fourth record, 64636. Now, this ID, even though it's different from 45876, when I place this value in this hash function, it will generate the same index position as the one that has been previously used by this ID. This is what is known as collision. So right now, for the first 3 entries, there is no collision whatsoever to worry about here. So that's why in this array, all 3 records are stored in the place that they should be, and making it very easy for me to access them later on. So all I simply have to do is, when I'm trying to look for a particular ID, let's just say, just for example, this index position doesn't only contain this ID, it's actually a record, it's a whole record. Now, this whole record will have, say, customer name, address, whatsoever, but to access that record, I'm only using what is known as the customer ID. So based on this, accessing these fields or this data can be very easy because there is no collision. I simply add this, I usually this use this ID in my hash function, and it will return my index value, and thereby I can access it directly. So there is no collision, and it's relatively easy to access all of these records. Now, when a collision does occur, for example, is for this fourth record, this is where things get a little complicated. Now, as we're discussing open hashing, this technique is known as open hashing. What we're doing in open hashing is that basically what we do is that we make sure that if there's a collision occurs, so for example, 64636, a collision has occurred. How? That the index position 6 is to be used for this ID, but index position 6 has already been used, in which case this is a collision. So what we do is that we start from the destined index position, which is index position 6, and start moving to the right of that index position until we find an empty space. So coincidentally, right now, as you can see in this array, I can find an empty space right after index position 6. So that means what I do is I proceed towards storing this record 64636 and index position 7. So I'll repeat it again. Basically, both 64636 and 45876 need to be stored on the same index position. But since 45876 was there first, it has taken up that slot. So this is a collision. Now, how do I store 64636? Well, I start off by searching for an empty space from its actual destined index position. So that means index position 6. Starting from this index position, I keep on incrementing my index position until I find an empty space. So coincidentally, since this array is not that filled yet, so I find an empty space right in the next place. And that's where I will store 64636. And similarly, if I get another fifth record, now assume that this fifth record is 23467. Now, according to the hash function, 23467 is supposed to be stored at index position 7. Now, if you remember that we just stored 64636 in index position 7. So here we have another collision. So the same rule applies. Start from the index position 7 and start moving towards the right until you find an empty space. So that's why at index position 8, I will find an empty space and I will thereby store 23467. And let's just say that another record came that had the index position 8 used reserved for it. But since 8 has already been used, I will proceed in storing 8 in index position 9. And if something comes by for 9, and I've already used the space for 9 for the record within this index position 8, but I've used it for 9, used the index position 9. So what I can do is instead of moving ahead, since I've reached the end of my array, I will come back and start looking from the start. This is known as the wraparound. So if I can't find an empty space at the end of the array, my algorithm will cause the index position to reset and start looking for it at the beginning. When searching for a record, we need to allow for these out of place records. Like so, it does not belong here, but looking for this is relatively easy because I'm actually quite near it. So this is what I meant by saying that we will allow some sort of linear search to begin. So that some sort of linear search occurs when there is a collision, and I will start searching for my destined record from the index position where it should have been stored. So yes, I am doing linear search, but that linear search is relatively small. And again, if I don't have any further spaces at the end of this array, I can opt for a wraparound and start searching from the start of the array until I find the record that I'm looking for. We know that if the record we're searching for does not exist in the hash table when it comes across an unoccupied slot. So it makes perfect sense. So assume that I'm looking for a record by the name of say 23. Say I'm looking for 33567. So according to hash function, 33567 is supposed to be at index position 7. By the way, this record doesn't exist. I'm not supposed to find it. I'm looking for something that doesn't exist. So by the logic, if I'm searching for a record using hash function, I will start looking at the position that it's supposed to be. So the hash function is telling me that it's supposed to be at index position 7. I go to index position and look at the contents. Are the contents the same as this? No. Go ahead. Are the contents the same as this? No. Go ahead. Are the contents the same as this? No, there's nothing there. Now, if say, for example, I started searching from the destined index position and I didn't find it, and because in search of that value, I started incrementing to the next index position, and say I kept on doing that until I found an empty space, and basically I reached an empty space without finding the record that I was looking for. What that means is that the record that I'm looking for doesn't exist. We know if the record we're searching for does not exist in the hash table when we come across an unoccupied slot. So you see 33567 doesn't exist. And how do I know that? I started from index position 7, not there, empty space. That means it will not be there at all. It can't be here anywhere because the logic says that if I'm using open hashing, I'll be here somewhere in an empty space, that the next empty space after the last recently used place. So there's going to be no gaps in between. So if I have encountered an empty space in search of a record, that means that record does not exist. So our algorithm will also be reflecting this part. Okay, now moving ahead. When searching a record, we need to allow for these out of place records, so on and so forth. And as you can see here, these are out of place. And finally, now let's see how this algorithm is implemented using the hash table as my array. And this is the size of it. The max size is variable, but whatever it is, it's basically just an array starting from index position 7. At each index position, we have a record type. So basically each record can have multiple items for a customer. It's not mentioned here, but basically it's a user-defined type. And what it means is that each index position has a record stored inside it, and we're accessing each record based on the key field, which is, by the way, the customer ID. So these are the previous knowledge that you have to have before discussing the algorithm. First, let's look at the process of inserting a record into the hash table. So by the way, again, we're going to use the term hash table to refer to the array where all of these records are stored. So the new record that I have just, I'm starting to store in my array will be passed as a parameter to my insert procedure. So that whole record is passed as a parameter, okay? So the hash function has been previously defined, kind of like something over here. See, this function has been defined over here. This hash function, exact same hash function, takes the key field, only the key field of this newly added record. Now, if you remember from paper 2, this dot notation was used to access individual fields of any record. So just to quick recap the format, or something like this: record name dot field name. So if, for example, I have a record something like this, type customer, name of type string, declare name of type string, then we have declare age of type year, or salary of type integer, something like that, and we do end type. Now we will start creating a record, new declare new customer, or new customer of type customer. And then, since we have created a record by the name of new customer, simply what we'll do is to access the name field of this new customer, we'll simply go new customer dot name is assigned with John. So this is basically what the key dot notation looks like. So that's exactly what we're doing here. So we're passing a whole record as a parameter into the insert procedure, and we're just simply applying the hash, and we're simply passing the key field of this new record. So assuming that we have customer ID here, like customer ID of type integer, and so on and so forth. And we're simply sending the customer ID as a function. So what we're doing is that we're simply accessing the key field, and the key field in this case is the customer ID. And in fact, it would have been called key here. It would have been called this way. So just the key field of the customer record to the hash function. And that hash function we just previously discussed is basically what? That we take the mod of that field by n plus 1. So if we have, say, 10 records or 11 records, so the mod would be of 12. If it's 10 records, mod would be 11. If it's 9 records, mod would be 10, so on and so forth. So what we did is that we simply passed the key field to the hash function. The hash function will return the hash value or the index position where that record is to be stored. Now, what I will do is that I will now start accessing my hash table, which I just mentioned a little while ago, is the array that holds all of the records. So I will start searching for an empty spot where, starting from where? The index position where I was just told by this hash function. So for example, if I'm starting to look for an empty space for this ID, the hash function told me to start from index position 6, and that's where I went. So that's exactly what's happening here, that I will start accessing my hash table from this index position, and I will move ahead until it is not empty. Now, if, for example, the hash function is empty, and I have found the place where I should be storing this data, and it's coincidentally is already empty, in which case this while loop will remain false, and I will exit it. I won't enter the loop body. So as you remember, we've studied this back in O levels as well. The while loop is one of those loops that may not run at all. So if, for example, this condition is false to begin with, in which case the hash value that has just been returned is actually empty, which means that this condition is false. So I will not enter to this in this loop. However, if it is not empty, that means I have to find an empty spot. So that means this condition will be true. And I have, for example, for 64636, I started at index position 6. It's not empty. So the condition is true for 64636. In which case, if it's not empty, if this condition is true and it's not empty, what I will do is I will proceed in incrementing my index by 1. And if the index has exceeded max, that means I have reached the end of my array. So that means I start looking for an empty spot at the, so this was full, and I have reached the end of the array, and I wrap around and start searching for an empty spot here somewhere in the beginning. So if I reach the end of the array, which means that I have exceeded the max place, in that case, I will start again, and by this, how I'll start again? Simply assigning index with 0, and I'll start searching from the very start until I find an empty space. And when I do find an empty space, this condition will become false, and I will simply exit. And after that, I will simply assign, when I exit the loop, I will simply access that index position because of which I exit the loop, and means that index position is empty, and simply access that index position and place that new record in that index position. And that's the end of this procedure of adding a record into my hash table. Okay, now as mentioned before, that since we are storing data, at some point we will want to access that data. We will want to access those records. So as mentioned before, that if you want to access records directly, it means that you will have had stored them directly. So that means that if we have stored those records using this technique, only then we can use the hash function to access them directly. Now this set of instructions, this is the algorithm that deals with finding a record in your hash table. Now again, the principle applies that the record that I'm looking for, I will have some key field for it. So what that means is that if I'm looking for example, a customer record, and the key field has to be unique. So best case scenario is that I would be accessing those customer records based on the customer ID. That customer ID will be sent to the hash function, and the hash function will tell me where that record should be. I will access that index position in the array, and I will either find it directly there, or if not, the next possibility is that I will have to increment to the next spaces until I find it. So while I'm performing linear search from that index position, there are two possible outcomes. Either I will find the record, or I will reach an empty spot. So if I reach an empty spot, that means the record that I'm looking for doesn't exist. And if, say, for example, I've reached the end of the array in pursuit of finding the record I'm looking for by incrementing one place after the other, I've reached the end of the array. This means that I'll have to come back to the start at the index position 0 and start searching from there. So either I'll find it or I will reach an empty spot. So using this principle over here, this algorithm is using the exact same rules. So first of all, the search, this ID, customer ID that I'm looking for, the customer record that I'm looking for, I will pass the ID of that customer, in which case the key field, to this find record function. That key field will be sent to the hash function, and the hash function will return the index position where that record most probably will be. Now, this condition is important here. So again, this condition is a complex condition, by the way. Secondly, as long as this condition is true, this entire loop will keep on going. How much? This part, all the way here. So what is the condition state? The condition states that if the hash table position that this hash function returned dot key is not equal to the search key that I'm looking for. So basically, if at the index position, the record that I just accessed, the key field for that record is not the same as the one I'm looking for. So if I just access the customer record in this index position here, if the customer ID is not the same as what I'm looking for, if this condition is true and the hash table that I'm at right now is not empty, and is there something's there. So if these both conditions are true, then I will keep on looking for it. So what that means is that the current position that I'm looking for does not have the record that I'm looking for, and there is still hope that the record exists because I have not yet encountered an empty spot. So if in search I have encountered an empty spot, that means the record doesn't exist. Now, if you see in this while loop, if this while condition, I may exit this loop because of one of two states. One possibility is that this condition becomes false. Now, this condition becoming false means that the index position that I'm just at right now, the key field is in fact equal to the search value I'm looking for, which means that this condition is false and I have found what I'm looking for. I will exit the loop. The second possibility, the second reason that I may exit the loop is because of this. Now, what this says that if I am at this index position right here, and it is in fact empty, it's not empty, it is actually empty. In which case, I have reached a spot that marks the last place where that possible, that possible index-related records may be. So what that means is that the record doesn't exist. So there's one of the two possibilities because of which I will exit this loop. Either I'll find the record that I'm looking for, which is this condition becoming false, or either the record that I'm looking for doesn't exist, because of which this condition becomes false. So either one of the cases I will exit the loop. But if this condition is true, it means that the search I have not yet found the record that I'm looking for, and I have not yet encountered an empty space either. So in which case I have to keep on looking. So how do I keep on looking? Simply, I go to the next place. I didn't find it at the default place. I will go to the next place and look there. And if, for example, the incrementation of my uh, index position results in it getting greater than my max position in the array or the last position in the array, that means I have to start searching from the start again. So wraparound has to take place. So in this case, if my index has exceeded my max, then I will simply initiate the wraparound feature by doing this and start from index position 0, like so. This is how I will keep on searching. So either I will, in the next index position that I encounter, same condition is tested, either I found it or not, or I reach an empty space or not. And if both of these conditions are true, I will keep on incrementing until either one of these conditions become false. Now, let's say if I have exited the loop. As mentioned before, exiting the loop is because of either this condition becoming false or this condition becoming false. So I have to ask this question. Did I exit the loop because of this condition becoming false? So what that means is if hash table index is not empty. So I left the loop because of this part becoming false, which means that I have encountered an index position which is empty. And by empty, it means that I did not find the, oh, sorry, if a hash table is not empty, that means it has data in it. So that means I have actually exited the loop because of this condition. Sorry, I mentioned this wrong. I meant to say that if this condition is true, it means that I exited the loop because of this becoming false, that I have actually accessed the index position, which has the key field as the same as a search key. So if I come out of the loop, this is the question I have. Is the place that I am right now not empty? If it's not empty, that means you exited the loop because you found the record that you were looking for, in which case you will simply return the whole record that you found at an index position. And on the other side, an else message should also be printed here. For example, we can add it here. The else state should say something like this. Else print not found. Something like this. It should be printed else print not found. So basically, if this is not true, that means I have exited the loop because of this being empty. Now that means I have to print not found. And that's basically how your hash table returns records that are previously stored in your array.